Hello everyone, this is Mrs. Lindsay Pereira. Today we are going to start our section on proofs with perpendicular lines. However, I would like you to do this warm-up, always, sometimes, never. And this should be a little bit of review here in terms of finding the distance from a point to a line here. I would like you to do these two problems and then push play when you're ready to check your answers. Okay, always, sometimes. I'm gonna highlight a couple of these real quick. One thing I want to point out to you again, I highly recommend again highlighting what they're referring to. So if I'm talking about B here, QT and WR, if I highlight those again, I'm extending them off the diagram. I want to highlight angle 1. So angle 1 is formed here, so I know I have this transversal. But again, it has to go all the way over to the parallel line. So that's only part of the angle. Same thing with angle 2. So the answer isn't never here. It's just not enough information. So that's why with an always, sometimes, never, that would be sometimes, because we couldn't prove that 1 is congruent to 2. We need more information. If they force you to say true or false, the answer is definitely false. And that's really what's going on with parts C and D as well. Okay. So that's why those answers are sometimes, not never. And again, if it's true or false, they would be false. This next one, hopefully you saw right away here that this line was perpendicular. So the distance from a point to a line, that is always the perpendicular line. That is the shortest distance from a point to a line. Okay, so some people in this triangle, we refer to that as the height. Which it absolutely is. In this case, since we knew the perpendicular and we knew the point it was drawn through, we could simply do the distance formula from A to D. Okay. However, there is a formula that will find distance from point to a line using standard form of equation. So again, standard form, a little review of what we did before. But you need to have it where the constant is on the left-hand side. So A, B, and C again are integers. Now, when I do x1 and y1, that's actually referring to the point. But this is referring to the line, ax plus by plus c. Okay? And then the A, the B, the C are referring to the A, the B, and the C in this line. Okay? But that will come up a little bit later in the homework, etc. Okay, we didn't have to do that here because again we knew this point of intersection. If we don't know this point of intersection, if that was not given to us, if we had no idea what it was, we would be using this distance from point to a line equation formula. Okay, so let's move on to some of our theorems and postulates here. If two angles are both congruent and supplements, so two angles are both congruent and supplements. So in other words, if it is given, angle 1 is congruent to angle 2, but that also angle 1 is supplementary to angle 2, then we can show that they are right angles. Or prove, I really should say. We could really prove that angle 1 and angle 2 are right angles. And hopefully this makes sense, because if 1 and 2 are congruent and they're supplementary, they both have to be the same measure, whatever that is, x and x. So add those up to 180, and then algebraically you could even get them to be 90 degrees there. Okay. All right. And it can be stated that same way there. If two congruent angles form a linear pair, then they are right angles too. Okay, because the linear pair is assuming obviously the adjacent. Supplementary is not necessarily referring to that. Okay, so let's move on to the next one here. In a plane, if a line is perpendicular to one of two parallel lines, then it's perpendicular to the other. So again, we have two parallel lines here, so we'll simply say M and N are parallel. So we're kind of given that. M is parallel to N. and then another line is perpendicular to one of them. So we'll say A is perpendicular to N. So that's what we're given. Well, then we can prove, or we'll know, right, however you want to say that the other line, so since A is perpendicular to N, it's also got to be perpendicular to M. And we can get that in a very roundabout way because we can do all the relationships knowing that these lines are parallel. We can do corresponding angles, supplementary angles, vertical angles. We get a lot of different relationships, but basically all of these angles in all these locations would be right angles. Okay, it's because the relationships of all the alternate interior angles, etc., that you get from parallel lines. Okay. And then the next one, if two coplanar lines are perpendicular to blank, then the lines are parallel. And hopefully you realize, oops, that this is same line. Same line. So again, let's kind of talk about this. Two coplanar lines are perpendicular to the same line. So if we're given L is perpendicular to, I don't know, B, and M is perpendicular to B. So here's B. And we'll say, okay, here's L, perpendicular to it. Here's M, perpendicular to it. Then again, we can prove, or we'll know, we can show all this, right? That L would be parallel to M. And again, very similar to the previous one we just talked about, we can get that by proving, again, corresponding angles, all the different relationships of the parallel lines. Okay, so if we know some perpendicular things with parallel lines, we definitely have some shortcuts that we can use when we're doing algebra problems, or when we're doing proofs. Okay, so let's try this one. Again, let's mark down our givens. AB is perpendicular to BC, so that gives us a right angle at angle B. DC and BC are perpendicular. Name all the angles that you can prove to be right angles. Please pause this video for 1 minute and answer that question, and then we'll go through it. So, only angle B and angle C can be right angles. You have to be very careful about things that you can assume from a diagram, and we've talked about this a few times before. You can't assume a diagram is drawn to scale. Okay, so let me draw this diagram in a slightly different fashion. Given the same information, this would still be true. You never would have looked at that diagram and said, yes, you have 4 right angles. Okay, you got to be a little bit careful with that. Again, what can you assume and what can't you assume from diagrams? Okay. All right, another one. I would like you to actually pause this one. And there is an E down here as well. In this one, try this one and circle your answers and push play when you're ready to check. Okay, and actually all of them work except for B. Pointing out just a couple different things here. The difference between A and C is literally they switch the order of the letters. So we have AC is parallel to BD. That would be true. We've got supplementary consecutive angles here, interior angles. And then AC is perpendicular to CD. So let's talk about this one. How is that true here? AC is perpendicular to CD. Well, because we know these all 4 sides are congruent, we can actually prove that this is a square. That comes a little bit later, but hopefully you know enough properties about that just from your previous work in some of the classes. Same thing here. This one we can prove that it's a rectangle because we've got these right angles and then the opposite sides are congruent. Okay, so let's try a proof here. Given AB is perpendicular to DA, and I'm going to go ahead and just start marking my diagram here. So AB and DA would mean that angle A is a right angle. DC is perpendicular to DA. That would mean we have another right angle. So again, if there's something I can write on the diagram from it, and it literally doesn't say angle A is a right angle, that would be my next step I'm probably going to have to do. okay? Let me talk about this. How do we highlight this? I'm going to just highlight it so I know that's what I'm trying to prove. AB, again, I always draw it off the diagram, is parallel, oops, sorry about that, is parallel to DC. That's what we're trying to prove, okay? So hopefully you see here when we have these right angles, we have a shortcut up here. So we don't have to say right angles. You could, but if we have two coplanar lines are perpendicular to the same line, then those lines would be parallel. So this is the proof that we're going to be using with that one. And I'll go ahead and just do a flow chart on this one. So we have AB is perpendicular to DA. That is given. And then we also have DC is perpendicular to DA, given. Again, we could say that they're right angles. We could go that route, but again, we have that special property because of the perpendicular portion of it. We can go right into saying that AD is parallel to DC. Two lines perpendicular to the same line implies they're parallel. Okay, so again, even though they've switched the order of DA and AD, these are exactly the same here, right? These are the same, so that means that they're going to be parallel. And I apologize, I wrote this. This should be B here, not D. AB is parallel to DC. Okay. Okay, so another proof here. Given EH is perpendicular to HJ, so let me go ahead and mark that as a right angle. Angle 1 is 4 times larger than angle 2. Prove that angle 1 is 72 degrees. So even though I said write this as a paragraph proof, hopefully you know you have to do that because you're going to use algebra to come up with proving angle 1 is 72 degrees. So let's go ahead and start with our givens here. It is given EH is perpendicular to HJ. I know I don't have the segments on there, but I'll put them on there. Therefore, angle EHJ is a right angle because perpendicular implies right angles. In addition, it is given that angle 1 is 4 times larger than angle 2. Here's where the algebra is going to come into play. So if I take this and I say, okay, angle 1 is 4 times larger than angle 2, I can now call angle 2x. Therefore, angle 1 would be 4x. So by the diagram, let me change that real quick, by labeling the diagram. So by labeling the diagram, which we did with x and 4x and algebra, we get the equation x plus 4x equals 90. And then we can go ahead and just solve that. So 5x equals 90. Divide there by 5. So we're going to get that to be, what's that going to be? 18. All right, what are we trying to prove? Well, we're trying to prove angle 1 is 72. Well, angle 1 is 4x, and we know x is 18. Since angle 1 equals 4x and x equals 18, then the measure of angle 1 would be 72 degrees. Okay? So again, whenever you're involving algebra within your proof, you must use a paragraph proof. Okay? And we label the diagram and use our algebra. And this concludes our notes on section 3.4, proofs with perpendicular lines.